appreciate the opportunity to present our research on using bulk wave ultrasonic standing wave to achieve individual propulsion of microparticles. My name is Wei Wang. I'm from Harbin Institute of Technology, Shenzhen Graduate School. I was trained as a chemist, so even the old hats are very new to me, and I'm still learning some old tricks. So to begin with, this is where our university is. It's a satellite campus of Harbin Institute of Technology, the main campus in Harbin. And it's located in the city of Shenzhen, which is right next to Hong Kong. The campus is founded about 13 years ago, and it's located in a university town, which also includes Tsinghua University and Peking University. It's undergoing a major expansion right now, and by the time it finishes next year, it will be housing twice as many people. So, in this talk today, I'll be talking about the story of how we made that discovery, that ultrasound can be used to propel metallic microrods into fast axial motion and spinning. And I will be telling what we know so far and what we don't know so far. So I'll be leaving some open-end questions to you guys. So our research group has been interested in knowing how to propel particles in various ways for a long time. And what we did was we make metallic microrods by something called electrodeposition. So we electrodeposit metals in template. Then we remove the template. We can make microrods of many different shapes and many different compositions. Once we have the rods, the first thing we discovered was it can move in chemical fields in 5% hydrogen peroxide. And it moves like this. If you can see the video, they move around like little bacteria. This was discovered about 10 years ago. And more recently, we found that we can use megahertz ultrasound to achieve something similar, more dramatic actually. They're moving more widely, about 100 microns per second. I'll be talking about this more. So here is our story. I'll be telling you how we got there and what we know so far. It started when my PhD advisor, Tom Maluk, went to France on a sabbatical trip. He was visiting Paris Tech, and he had a friend, Dr. Mauricio Hoyos, and they were talking about doing some ultrasound experiment with all sorts of particles. And we were able to make metallic microrods, so he asked for some sample. And he did the experiment in an acoustics chamber, which is very simple. And he put a few Kapton layers on a plate, which is hooked to a transducer. And the ultrasound wave is going this way. So, and this is inside the chamber. And if you hit the right frequency, and in the system it's about a few megahertz, you will have a standing wave. And at the center of the standing wave, you have a nodal plane. Whenever you have a particle in this kind of setup, they will start to levitate onto this nodal plane and move around. And this is what I mean by old hat, because this is nothing new. There's classic literature that talks about this phenomenon. However, a lot of the study focused on spherical polystyrene particles. And what we did was we had these metallic microrods, a few microns long and a few 100 nanometers in diameter. And we had those in the system, and we saw something completely surprising. So in this video, the first thing you see is the one I showed before. All these particles are moving around. This is real time, about 200 microns per second. And the other thing they would do is they would start to spin around. And this is more striking, and they will form this spinning chain. And these chains would spontaneously and dynamically interact with each other. So you can actually see all these individual particles are still moving along the chain. And this chain actually belongs to a bigger structure. If you zoom out, as you can see in a few seconds, if you zoom out, this chain is part of a big ring. And on this big ring, all these individual particles are shuffling around like on a conveyor belt. So a quick summary, what you just saw was all these metallic microrods on a levitation plane, and at the right frequency, you will have them aligned into chains, and the chain will start rotating, and you have them moving around really fast. You also have this big ring structure. So we started asking the question. We started doing more experiments, and we found that we can modulate their motion by changing the wave amplitude and change the frequency. And also, there's something else we found. Both the shape of the particle and the composition of the particle really matter. For example, if you make a particle that has round edges versus a curved edges, the one with curvature will move, but the one with round edges would not move. On the other hand, if you make a rod out of polymer, they will not move at all. Only the metallic rods will move. The other thing we did was quite interesting. We actually mixed all these rods with live cancer cells, and then we could use ultrasound to move these rods within cancer cells. So they were still responsive to ultrasound, even when they're within cancer cells. And this was actually picked up by a lot of news media, and got something like 500,000 views on YouTube. And if you believe anything from YouTube comment section, which by the way you don't, is that these guys will destroy us because they get into cells and turn our body upside down. Okay, so the question we started asking ourselves is, why does ultrasound move these metallic microrods? And the first thing that popped up in our heads, as a chemist, you know, nothing you make is perfect. They always have some sort of defects or asymmetry. So we went back to the SEM image of our rods, and we found that these rods always have a concave tip. So this is the rod. At one tip, it's curved in. There's a concavity. So this curvature from fabrication made us think maybe this is why it's moving. And the reason is, okay, so there's another experiment that shows the one with more concavity actually moved faster than the one with a flatter end. So it got us thinking maybe it's because the asymmetric shape will scatter sound wave asymmetrically. And then we have a distribution of acoustic pressure along the rod, which propels the particle. So this is the first hypothesis we had, and it's being proposed for a while. So the second hypothesis, someone else proposed by Dr. Laga, was based on an asymmetric streaming model. And he proposed that if you have a particle that has asymmetric shape, and this particle, this is his own word, we showed how the transverse oscillation of asymmetric shape gives rise to a propulsive force. In summary, he's saying that this particle is oscillating, and that oscillation is causing a streaming flow on this particle, and that because the particle is asymmetric in shape, that streaming is asymmetric, and that streaming will cause this particle to move in one direction. The third hypothesis was actually coming from a group of active matter physicists, Dr. Ramaswamy, and he had an experiment where he had a macroscopic rod of asymmetric shape, and the rod is actually moving on a vibrating surface. So the surface, this video won't play, but the rod is actually traveling on a surface. You're looking from the top. The surface is vibrating, and the rod is moving forward. And his theory is the rod is moving forward because the rod is vibrating asymmetrically. And this is actually very relevant to our system because we also have asymmetric rod on a vibrating surface. Here, the vibrating surface is just a layer of water, but we could have a very similar effect. So none of these three hypotheses has been proved or disapproved. We are still in the middle of experimentally verifying each of these hypotheses. So in conclusion, I've told you the story of how we made the discovery that we can use megahertz ultrasound to move particles into directional motion and also axial spinning. I've shown you that both the shape and the composition are very important. And the speed of the particle is very sensitive to how strong the wave is and what the frequency we're applying. We don't know yet what is propelling the rod and why they align to chains and why the chains spin. Maybe someone from the audience can help me with that. With that, I would like to conclude the talk, and I would like to thank all these